It's okay. Can you
Yeah.
watch it?
Can you minimize the Zoom? Minimize because we can see your Zoom, not the presentation.
Okay.
No, we cannot see. Yeah. Now please make it full screen.
Okay, I'll start my
F5.
presentation.
Oh, okay. Yeah, please
Okay.
open. Yeah, now we can see the screen. Please start.
Hello, everyone. I'm proud to present my work. My English is not very well, so there may be some. Okay, let's begin. The subject of my presentation is LEA-DNS. DNS resolution, validity, and timeliness guarantee local authentication extension with public blockchain. The presentation will include 5 parts: introduction, overview, design, cost analysis and evaluation, and conclusions. First, introduction. DNS is a distributed database with a centralized data governance model that maps the names to values online, primarily controlled by the Internet Corporation for assigned names and numbers. In this regard, it manages the top-level domain and therefore controls the root name server. In practice, if a client wants to contact a host with a specific name, it must first send a query to the DNS server to obtain the host's IP address. In order to improve efficiency, the DNS server may maintain a replica of the information in its cache based on how often the domain name is requested. In the case that the DNS server does not hold the requested knowledge, the query will be propagated to the root name server. Next, the basic name server will find the server of the corresponding TLD and then forward the query to the corresponding authority name server, which may retain the requested IP. Due to its centralized management architecture, DNS root is vulnerable to many attacks. The current issues facing DNS can be divided in 2 categories: centralization problem and the data authenticity problem. The centralization problem is that because users default to avoid DNS root servers being trusted, there will be malicious servers to attack. The failure of this trust anchor is far more than a theoretical threat. Distributed denial of service attacks are another threat. Cache poisoning and renumbering injuries are also related to centralization problem. The data authenticity is that clients have no choice but to trust the resolution results unconditionally. Thus, if manipulated results were returned by some bogus or compromised name server, clients will not be aware of that. Because of the decentralization nature of the blockchain and the untamperability nature of the data, the DNS resolver only needs to provide proof of the existence of the information in the blockchain, and the local browser can effectively solve the problem of DNS centralization and data authority by running the verification program. However, the blockchain is an add-only database, and an attacker may provide an outdated proof of existence to spoof the client to achieve the attack. As shown in figure, an old TX transaction can have all the block headers stored by the light node. Then the SPV can be used to prove its existence. However, if a new transaction, new TX, is based on old TX with modifications, old TX is still correct. But we cannot prove that the old TX is the latest unless we download the whole chain to verify that there are no further transactions. Attackers may take the old TX to trick users. These are my contributions. First, design a UTXO-based structure for storing and transacting DNS name-value pairs to fit our system design. Second, simplify the blockchain design applied to stateless blocks as a public blockchain database for storing key value pairs. Third, design a system called LEA-DNS that allows users to perform enhanced verification of domain name resolution result locally. The system not only verifies the validity of the data, but also the timeliness. The last simulated experimental results show that each DNS response with verification does not exceed 3.052 kilobytes in size, and only a small amount of data needs to be stored locally. Local validation time takes less than 10 milliseconds. As shown in the figure, LEA-DNS is composed of 4 main components. Tree structure DNS. Here is the traditional tree architecture domain name system to maintain good compatibility within the LEA-DNS. It can be deployed directly without any modification to the current DNS architecture. In other words, LEA-DNS is transparent to the current DNS. Name Value Blockchain Database, NVBD, is a decentralized way of storing name value pairs that require enhanced validation. DNS Bridge is a set of proxy servers that handle requests and provide a verifiable DNS response. Client can firstly request services directly from the traditional DNS. Secondly, it can send a verifiable request to DNS Bridge as step 2. In step 5, the client needs to maintain communication with the NVBD at the same time, but only needs to synchronize the latest block headers and save a small amount of other data to verify the transaction locally about guaranteeing validity and timeliness. If the validation fails, the error proof message is submitted to the NVBD as step 6 in figure. This part focuses on the technical details, including transaction design, the block structure of NVBD, DNS bridge, and client. There are 5 operations of DNS in transaction. First is register name. Domain name provider A first needs a raw transaction as its initial transaction as shown in figure TX0. When A needs to register a domain name, it takes the raw transaction as input and outputs a transaction of type name regist. The output contains the domain name field. If the domain name is duplicated, the transaction will not be packaged into the block. Second operation is set value. Set name value. Assigning a value to a registered domain name or transfer domain name is known as an IPv4 address in LEA-DNS. Delete value. When A needs to reassign a value to a domain name or to transfer a domain name, A needs to enter a transaction of type set value and generate a delete value type of transaction. The original assignment is deleted. Transfer name. Transfer of a registered domain name. When A needs to transfer its domain name to B, A needs to enter a transaction of type name regist or delete value and generate a transfer of type transfer name transaction, the output address of which is the hash of the public key of B. At this point, the public key of B is not public and is anonymous to a certain extent. The 5 operation is update value. The value update operation is similar to the domain assignment operation. Its input and output are both a transaction of type set value. Now I'll introduce the block design. First, we'd like to understand about accumulators. Basically, a cryptographic accumulator is an algorithm to mix an outsized set of values into one short commitment. and enables to compute a brief membership witness or non-membership witness of any element that has or not been accumulated. RSA accumulator is predicted on modular expansion under the strong RSA assumption. TXOC is a commitment for all transactions. Traditional verification can check the Merkle path from transaction to TMR directly, but this requires the verifier to store all block headers. To reduce the verifier's storage overhead and speed up this verification approach, we use the MMR approach, Merkle Mountain Top approach. The user only needs to store what the MMR picks in figure A, provided with the Merkle path from the transaction to the TMR and the Merkle path from the TMR to the MMR route, which is constructed by MMR picks. The number of MMR picks increases logarithmically with the length of the blockchain, so this overhead is small. DNS Bridge is required to synchronize all of NVBD's block information and update the DNS and the transaction map information based on the transactions in the block. It forwards the user's DNS request and finally form a verifiable DNS response back to the user. In order to let user verify the validity and timeliness of the returned name value pair, it is necessary to generate the validity and timeliness proof of the set value type of transactions corresponding to name value. A validity proof of a transaction is a proof of the existence of a transaction in the blockchain. The proof of existence of a transaction is divided in two parts. Merkle path of the transaction to TMR, the Merkle path from TMR to MMR route. Timely proof TFM-XN is a proof that transaction XN is not used from block N to block M. Delta TFM-XN means in the latest delta blocks, the transaction XN is not being spent. With the growth of the blockchain, will become out of date. Assume the current block height is M. In order to update the proof, we can calculate the proof, and a new proof can be computed based on the old proof. The client receives the messages returned by DNS Bridge and can verify the validity and timeliness of the message content. Validity Verify. Initially, users are required to download all MMR picks collections. After that, the MMR picks collection can be updated by itself each time a new block header is synchronized. The Validity Verify is divided in two steps. First, check if the Merkle root of MMR picks is equal to the TXO commitment of the latest synchronized block header. If it is equal, proceed to the second step. Otherwise, resynchronize the block and check again. Check Merkle second step. Check Merkle path from transaction to TMR and the Merkle path from TMR to MMR picks. If so, the verification is passes or succeeds. Otherwise, the verification fails. The user receives the timely proof and the block header where it is located. The existence proof has been verified by validity proof. We extract the accumulator field STXOC from the block header, the latest block STXO commitment, timely proof, and the transaction that needs to be verified as parameter inputs as shown in algorithm 3. The algorithm can be verified, the proof can be verified similarly. But the input block header is block n minus delta rather than block n. We use the RSA accumulator with, now I introduce the experiment environment. We use the RSA accumulator with 3072-bit modulus, 128 bits prime presentative, and the Merkle root is set to 32 bytes. We run all our experiments on our desktop computer equipped with this, and perform 10 runs and report their average for each data point of running time. Here is some parameter and the description. We note that for convenience, we assume that each transaction will consume one input and generate two outputs. The average number of UTXOs consumed per block will be m divided 2. The accumulate needs to be updated for each transaction in the block, and the time complexity of the update is the update of the accumulator in a block can be divided into the process of calculating the product of all transactions using the function and the process of product modular exponentiation. The experimental results are shown in the figure, where the time grows linearly with the number of transactions in the block. DNS Bridge needs to synchronize all the data of NBD with STM at SH scale each block generation, so the synchronization bandwidth between DNS Bridge and NBD must be at least here. If we use the Bitcoin parameters, it only needs about 2 kilobytes per second bandwidth. However, it needs to provide service for clients with high bandwidth. This is performance of the MMR operation with the blockchain growing. This is the performance of the timely proof generation. This is the performance of the timely proof verify. From calculation, the size of the validation date is less than 3052 bytes, and the date size for synchronization will be less than 9440 bytes. This is a conclusion for time complexity and cost time level. Here is the conclusions. My presentation is over.